Alyssa, it was really nice to meet you today. Okay, so I've done some digging on the pressure standard. I just wanted to make sure that I was telling you the right thing, not leading you astray. Yeah, so obviously we talked about this is the manometer, and so this is where we're trying to find pressure of some unknown. All right, and we're comparing it with this open end, and the open end, of course, would have just air pushing down, and we know the pressure of air. All right, so talking about these units, mmHg is a unit that we need to be in here. And so if you're in a different unit, you want to convert to mmHg. And at the top of the document, it talks about doing those conversions. Okay, so we're already in mmHg, so we're good to go. So actually, just like we talked about, just wanted to, double check. All we're looking for is the difference. So we have 127 minus 84, and I could do that in my head, but I'm not going to, is 43. And we see that in this case, this unknown pressure is pushing down more than air. So it's going to be 730 mmHg plus 43, which gives us 773 mmHg. It's pushing down more than air, so here's the pressure of our unknown. If we have a situation like this, where we're pushing down less than air, so air clearly pushes down more than the pressure, well, the difference here is going to be 130 minus 26, so 104. So for B, it's going to be the air, but minus the difference, because I can see my unknown has less pressure. It's pushing down less on the side of the U-shaped tube. So 730, again, I can do this in my head, but when I am being observed or making a video, I don't know, my ability to do mental math flies out the window. All right, so I hope that helps with those. And then we did not get a chance to talk about barometers, so I just wanted to quickly review this as well. And we did mention we measure atmospheric pressure with a barometer. Pressure is not the same everywhere on Earth because pressure is measuring how much particles push down on Earth. And we actually have more particles closer to Earth and fewer particles further up, if we were to think about like a column of air. So there's more pressure closer to the Earth and then less pressure up here. That's why if you go up to altitude, well, we know there's fewer air molecules, like it's harder to breathe, less oxygen, and also there's less pressure, like it is, you have differences in cooking because there's less pressure, and so that changes actually the boiling point of water a little bit. Lots of stuff going on there, super cool. But anyway, atmospheric pressure is not the same. Altitude changes it. Temperature can also have an effect there. So we use mercury rather than another liquid. Mercury is great because it doesn't really evaporate. It has a really low melting point, really high boiling point, which is not true of water. You could imagine a barometer in, a cold place, all of a sudden it has ice in it, not so great. That's not going to happen with mercury. But really the big deal that we use mercury for is because of the height of the barometer. The height is the thing that matters, not the diameter, because pressure is force times area. This is super physicsy, but we account for the area by just measuring the area. So it doesn't matter what the area is. It's just going to be the force pushing down in the area. So the diameter doesn't matter, but the height does. So this is a very physicsy equation that I've shown you here, but the P of the atmosphere we can find. So we can just be given it like we were here, but we would calculate it using a barometer by taking the density of whatever's inside, usually mercury, multiplying by this constant, gravity, the force of gravity, which is just 9.8 meters per second squared, times the height that we have in our barometer. So I know this says inches. Usually we would use SI units, but the way a barometer works is it's open to the atmosphere, and then this is going to be a vacuum. And so the atmosphere is pushing down on the mercury, and because this is a vacuum, it pulls the mercury up, and it's going to pull up based on how much it was being pushed down on by the air. So then we can find the height of the mercury height, and of course it's the force of gravity pulling these down, pulling the particles down that end up doing the pushing, right? And then times the density. So how much it gets pushed up is going to depend on the density of the liquid. Okay, so they ask us, what is the maximum height of mercury in a barometer? 760 millimeters, while that of water is, so if I use mercury, my maximum height is this. For water, it would be 10.3 meters. Well, that's because of this formula, because mercury is, I'll just use the symbol, mercury is Hg. Mercury is, Hg, is 13 times more dense than water. And so this number is way bigger. That means that mercury, this number, or the height, for mercury can be way smaller. If I were using density of water, well, then I would need a much bigger height to measure the atmospheric pressure. So they actually ask you to use this formula. I know it's a physics formula, but they give you this calculation to do. If the density of air is 1.2 grams per liter, again, density just goes in to where we have this pressure, 1.2 grams per liter, gravity, 9.8 meters per second squared. Estimate the height that we would have, height, and pressure of the atmosphere. They give this to you up above in that same document, and they're expressing it here in pascals, and pascals are the units that are going to work out with the other units that they give you. So the height that we get there, it ends up being something like 8,000 kilometers, and they're asking you, is this a good height for the whole atmosphere? Like if I had Earth here, and then I were looking at the height of the whole atmosphere. So it's an estimate, but it doesn't take into account what we said here, that atmospheric pressure changes over the course of the atmosphere. So that would be the assumption that you're making, that that this force of gravity doesn't change because of altitude, and that the densities aren't changing. All right, I hope that helped, and good luck on your test tomorrow.